All right, so the next thing I want to show you is C504, which is more of the same mathematics. C504 is factoring large numbers. And we're going to just do essentially the same thing. The only trick here is you have to do a division, and you have to learn how to avoid having that division go down to imprecise floating point mathematics. You have to get accurate square roots. So let's start with this. I'm going to use interactive Python for this one, Python 3. All right, so here I can take a number 1001 is A, and then I can multiply it, and I get this square correctly, of course. Now, let me move this over. I think it'll do. All right. So now I'm going to make a large integer, 10 to the 100 plus 1. And let me try and make these both fit on the screen a little better. All right. So 10 to the 100 plus 1. And so if I print A, it goes all the way across the screen. And if I print A times D, they call it floor division. Exactly. Yep, you got it exactly. Slash is what you need. That is the magic secret. So A times A is now 200 digits long, and it's got it accurate right down to the 1 at the end. So that's what I mean. Python handles arbitrarily long integers and does it precisely. As long as you make sure it's doing integer math, it will do it with complete precision. But if you want to do a square root, that's a complicated calculation. And you can do it with math.square root. So here I take 10 to the 100 plus 1. I set b equal to the square, which we just saw up there. Now I calculate the square root of b. And what I get is 10 to the 100, and that's wrong. It's 10 to the 100 plus 1. So the square root library is not accurate to 100 places, 100 decimal places. It's doing some kind of floating point approximation, which does not go far enough. So if you want an accurate square root, you have to use the decimal library. This is a library that lets you specify how many places you want to have. So you can set the precision to 200 if you like. And then it will do floating point math to that precision. So this is one way to be highly precise. And wait, I got the wrong copy. Okay, let's try this again. There. Now I'm going to take B is 10 to the A is 10 to the 100 plus 1. B is A times A, and now I import everything from the decimal library. I set the precision to 200 digits, and now when I do the square root, I get the right answer to 100 places because I set the precision to 200 places, and you can see it didn't really take too long. There wasn't a long pause or anything, so Python's fast enough to act in high precision if you tell it to. So that's one thing to do, and so here we're going to get the factors of this number. So we set n equal to that number, and we're going to start with the square root. So here is a plan. Now, by the way, if you have an arbitrary p and q and you create n, there is no way to factor it. Okay, that is the whole point of RSA. You can't factor if you choose p and q randomly, and therefore they're not particularly near to each other. However, if you use companion primes or other primes that are close to each other, then you can factor it. And that is something people do in capture the flag problems and sometimes by accident. It would not happen in a proper library to generate your keys. It's one of those mistakes, like I say, you'll find out you're making if you try to write your own crypto. So here I have a number which I'm trying to factor. And you can kind of tell from all these zeros that I did take two numbers that were very close to the square root. And so now I set my precision to 50 because this is only 50 digits, I guess. And then I do the square root. So now I have the square root is here. And you can see the square root is almost perfectly an integer, which is another clue that I really took two numbers close to the square root. So this 1 and a whole lot of zeros and then 83 is the integer part of the square root. So one of the two numbers, which by tradition is p, the smaller number, must be lower than this. And the other one must be higher than this. And you could search for either one. But what I'm doing is starting with this 1, a lot of zeros, and 83. I define n. This is how you do a hunt to factor a number if the p is close to the square root. What the clue here? Oh, you see all these zeros. For this number, this is the product of 10 to the 100 and 10 to the 100. So it has a lot of zeros. And the fact that this has a lot of zeros shows you that I took two numbers that were just one with a lot of zeros and a little small change at the end. So I had 1 plus a small number. Here's the small number squared, and here's the twice the product of the two. You know, let me make a little note here. If you do physics, you always look for the small parameter. So if I have 1 plus epsilon, and then I square it, I get 1 plus 2 epsilon plus epsilon squared. And in this case, since I used numbers with a lot of zeros, you can see those three pieces. I used, in this case, I used something like 1 and a whole lot of zeros plus a small number like 33 squared. And the end result of that is going to be, you're going to get 1 and a whole lot of zeros. Then in here, you're going to get 66. And then you're going to get a lot more zeros, and then you're going to get 33 squared at the end, whatever that is, like 169 or something. That's all I'm saying. This structure, you can actually see these three parts separated by zeros, 1, 2e, and e squared. That's all I'm saying. That's the clue that this number was actually created by using a number that was very close to just 1 plus 10 or 15 zeros. That's how I made it, basically. Anyway, so now I'm going to start at, define p0 to be the square root, and define n here. So now I'm going to start at the square root, and I'm going to try going down by 2's, because there's no point trying even numbers. They're never prime. So I'm going to jump down through the odd numbers, and I'm just going to calculate p and n modulus p. And these are perfect integer mathematical calculations. N modulus p will be done with high precision. That's all. So this is the p, and this is n modulus p, and you see it goes down, 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 and then it hits 0. So this is where the modulus is 0, which means n is factored by p. So this is p. And here's the square root, and you see it was only like 30 or 40 below the square root. So that's all you have to do to factor a number that is almost a perfect square, where p and q are similar. And q will be just similarly up high, and we can find q by just dividing, of course. So let's, now I know n and I know p. So, oh, it didn't do my copying, right? All right, try this again, copy. All right, there. All right, so now I have my n and my p. So q is n over p, and as someone put in chat, you use 2 slashes here. If you used a single slash, it would go to floating point mathematics, which is approximate, and that's not what we want. 2 slashes will do so-called floor division. It will divide by it, and if it's not an even number, it will round it down to the integer below that. So the end result is an integer. And so I get q. However, that means it's possible, if this didn't really make an even division, my q might be wrong, so I like to check it by printing p times q and n minus p times q to make sure that it really is 0. And so it really is 0. So I found n and I found p, and now I have q. So now that I got p and q, I can calculate everything like phi and all that jazz. I'm in business. So you got a number to factor, and then you got another number that's really pretty long to factor. And off you go. So again, a little bit of mathematics to do.